Hey there, Calc folks. Back here with another video in our study of vector-valued functions. We're at the point in our study where we want to take note of the fact that we are dealing with something that's behaving functionally, right? And as with the idea of a scalar value function, right, we can apply we can apply our calculus operators to a vector value function very much like we have been applying our calculus operators to scalar valued functions, right? Vector valued functions are different from scalar valued functions in terms of form, but with regards to some of the things that can be applied to these function types, we have some very similar types of operations. For example, in the calculuses with a vector valued function, we can actually take a vector valued function and apply limits, we can apply derivatives, and we can apply integrals. And we can look there at the calculus of our vector valued functions. Well, what we're going to want to take a look at today is the calculus of the vector valued function, right? And get into the limits of vector valued functions. So, folks, that's where we do begin here. We are going to be looking at limits of vector valued functions in this quick little set of notes. And where we do start our study is going back and recalling our early days of calculus back in chapter 2, I do believe it was, where we were introduced to the idea of a limit, right? Where in the introduction to a limit, we approach limits with the following idea, that if we had ourselves a scalar valued function known as f of x, that we could come along and apply to that function a limit operator as x approaches a in that operator. And we denote that by saying this here mathematically. The limit as x approaches a applied to f of x, right, equals the value of L, right? And we can say the limit as x approaches a for f of x equals L, right, when we have the case that f of x becomes arbitrarily close to L in value as x becomes sufficiently close to a in value, right? Keep in mind what a limit does describe in general is behavior of a function. All right? A limit tells us how does a function behave as the independent variable in our function behaves a particular way. Right? Our independent variable is going to approach this value of a, whereas our function is going to approach some value of L, right, as the dependent value. And when that happens, we have the limit as x approaches a for f of x is equal to the value of L in the case of a scalar valued function. Well, we see something very similar in the case of a vector valued function. Right? In the case of a vector valued function, if we have this vector valued function r bar of t, we can apply a limit operator as parameter t approaches a in value to that vector valued function. And what that does look like is this statement here. Here we have our vector valued function r bar of t, where we are applying this limit operator to that function where the parameter t is allowed to approach the value of a. And we can say that all that equals L, right, if it is the case that our vector valued function at the value of t becomes arbitrarily close to that vector description L in value, as parameter t becomes sufficiently close to a in value. All right? Here we're describing the behavior of a vector in this limit. How does the behavior of this vector behave? Right? What is the behavior of this vector as the independent variable or parameter t approaches this value of a? Right? And if the vector valued function approaches the vector L, we can say that that vector L is the behavioral description for our limit. It is the value of our limit. All right? Now, back in Calc 1, when we defined the above, we used the epsilon delta definition. We do move beyond that a little bit in the context of vectors, because vectors do talk about position in space, right? We're able to summarize this behavior and position in space using the following definition and avoid some of that epsilon delta necessity. All right? Note here, this definition is rather short. It just says, note, the limit as t approaches a for r bar t equals vector L, provided that if we look at the limit as t approaches a for the absolute difference between these two vectors being equal to the value of 0. Now, the absolute difference between two vectors is itself a vector. And I believe what I am actually missing here is I should say this is not equal just to 0, but is equal to the 0 vector, if I'm not mistaken. Let me just double check that. Keep in mind, our book does not use the bar notation. It uses now let me The book has a scalar value of 0. But I'm questioning the authenticity of that, the accuracy of that. Questioning the accuracy of that because we are looking at the difference of two vectors. Right? The absolute difference of two vectors. But essentially, the positive result of taking the difference of these two vectors. And what is the difference of two vectors? Well, it's like adding an opposite vector to another vector. And adding any two vectors together always produces a third vector. Right? So this 0, I do believe, should be a 0 vector because we are looking at the, in a sense, sum or difference of two vectors, where we understand the sum or difference, the behavior for a sum or difference of two vectors is itself a vector. All right? So we are looking at the limit of another vector-valued function given by this difference, which should, in a sense, be itself a vector-valued function implied by the definition. So I'm going to say this is provided that we are dealing with the 0 vector. In a sense, what we see happening here is we do have our vector, in a sense, if we think about my finger being this vector in space r bar at t, as t approaches a, right, this vector is going to behave a certain way in space. And what that vector might actually do is start to approach vector L, right, in value. These two vectors are going to, in a sense, approach vector L in value as t approaches a. And if vector L and vector t, r bar at t, are in a sense the exact same vectors, their difference, the vector that's the difference between the two, is essentially the 0 vector in size. All right? And if we see that occurring, we're able to say that the limit as t approaches a for r bar t is equal to L in value. All right? Now, we rely very little on this understanding to evaluate limits of vector-valued functions. This is how it's defined, though. Right? To go back and really to begin calculating the limit of any vector, or limit of any function, vector value or scalar, we do really go back and sometimes rely on these ideas, right? Where the function becomes arbitrarily close to some value as the independent value becomes sufficiently close to some value, right? That really is the way that we go about looking at limits, right? Now, in terms of calculating these for, though, a vector-valued function, it is a rather intuitive process. I do give you this note. As for applying the limit, note in R2, if we have this vector valued function given by r bar of t equal to x of t comma y of t for our components, the limit as t approaches a for r bar of t is really just going to be the limit as t approaches a for that vector, that two-dimensional vector function x of t comma y of t. Where how does the limit behave when applied to a vector valued function? Well, this line indicates that that limit will just distribute itself across the components of the vector valued function. The limit will apply itself to the first component x of t, and we'll be interested in the limit as t approaches a for x of t, that scalar valued function x of t, and that limit as t approaches a will approach y of t. And we'll become interested in the limit as t approaches a for y of t for the y component in the result of our limit's value. Similarly, in R3, if we add in a third component to our vector description, when we apply that limit again will just distribute itself across all components. And we will see the limit as t approaches a for x of t is the first component. The limit as t approaches a for y of t is the second component. And now for the third component, we would have the limit as t approaches a for z of t. All right? To apply a limit to a vector valued function, you are just going to distribute the limit to the components of the function and evaluate the limit for the scalar components of the vector valued function. All right? Let's illustrate this with a quick example where I am going to help you recall a couple of important ideas from limits also here, folks. Excuse me. Consider the limit now as t approaches a Sorry about that. I got a coughing fit there. Consider again finding the limit as t approaches 0 for r bar of t, where in this example, r bar of t, let me clean this up. All right. R bar of t is this two-dimensional vector valued function where the first component is 1 minus e to the t divided by t, and our second component is t raised to the power of 2t. All right. What we noted from the application of limits to vector valued functions is that when we apply the limit to r bar of t given above here, we are going to just be applying the limit to this vector two-dimensional vector valued function, where that limit operator is just going to distribute itself across the components. Where to evaluate the limit of this vector valued function, we now have to evaluate the limit of these scalar valued components. All right. In terms of evaluating the limit of the scalar valued components, let's start with this first calculation. We can note this might require a little L'Hopital's rule. All right. When we attempt substitution, substituting a 0 into these locations for t, well, certainly that's going to produce a 0 in the denominator through substitution. And when I plug in 0 into for t here in the numerator, e to the t is going to be 1 in value, and 1 minus 1 will also produce 0 in value. And since this limit from substitution results in the indeterminate form 0 over 0, we can apply L'Hopital's rule, which says what we're really then going to be interested in terms of value is the limit as t approaches 0 for the derivative of the numerator over the derivative of the denominator. Now, if I take the derivative of 1 minus e to the t, that is just negative e to the t. And if I take the derivative of just t, that is just the value of 1. And if I now consider the limit as t approaches 0 in that quantity, that is nothing more than negative e to the 0 power. And what is e to the 0 power is just 1, so this is really just negative 1 in value. Right? So the value of this first component's limit is just simply negative 1. All right? Whereas if I consider the limit now as t approaches 0 for t to the 2t, one thing we point out early is that this is going to require a little bit of L'Hopital's methods. Since when we attempt substitution into this format here, we do end up with that indeterminate form 0 raised to the 0 power. 0 raised to the 0 power is an indeterminate form, that if we go back and recall is going to require us to apply some L'Hopital's methods. And what L'Hopital's methods tells us, right, is that the limit we're going to be interested in is nothing more than e to some power of L. Where the value of L that we're going to calculate here is really just going to be the limit as t approaches 0 for that power of 2t, right, times the ln of the base found in this power, right? Remember, if this is the form f of x raised to the g of x power, in L'Hopital's rule, it's going to be g of x times the ln of f of x. Well, g of x is 2t in this case, and f of x is t. So it's going to be 2t times the ln of t. Where from L'Hopital's methods, we could note that is going to give us 0 times negative infinity, which is more L'Hopital's methods, which says arrange this into a ratio that produces either infinity over infinity or 0 over 0. And I can move the t to the denominator and to form that ratio, and think of it as being t to the negative first power. And what I end up producing here then is the case for infinity over infinity from substitution, where I can now apply L'Hopital's rule. And again, from L'Hopital's rule, it says that L, this value of L I'm interested in, which is just the limit of this ratio, can be thought of as being then the limit as t approaches 0 for the derivative of this numerator over the derivative of this denominator. And if I take those derivatives, those are quick calculations. In the numerator, that is just 2 over t, or 2 times 1 over t. And in the denominator, that becomes negative 1 over, or I should say negative 1 times t to the negative second, or negative 1 over t squared. Where if I clean this up a little bit, moving that t squared back to the numerator and canceling with this t in the denominator, it does become the statement negative 2t in value. So really we're just interested in the limit as t approaches 0 for negative 2t, which is nothing more than 0 in value. All right? So the L, right, that we're interested in the value of our limit's value being e to that value of L, is going to be 0. And thus, if we think about the limit of interest, it's just going to be e to the 0 power, which is nothing more than the value of 1. And thus, in the end, the limit as t approaches 0 for r bar of t is nothing more than the value negative 1, comma 1 in value. All right? Since L is equal to 0, we know the limit of interest here, the limit of the second component in our vector-valued function, is going to be equal to e to the L power, which is equivalent to e to the 0 power, just 1. And thus, we're able to substitute that value of 1 into the limit of our vector-valued function. All right? So, folks, that is a quick example of applying limits to vector-valued functions. It's a rather intuitive process. There's no fancy rules there. The limit operator just distributes itself across the components. All right? And the result of the limit for the vector-valued function is going to result from applying the limit to those components. All right? Some things you want to keep in mind, though, with evaluating limits is you want to remember things like limits at infinity and infinite limits. Those all come into play here also. As well as these cases for what? L'Hopital's rule and L'Hopital's methods. Right? Those were back in Calc 1. So these and were reviewed in Calc 2 and come back here in Calc 3. We cannot forget our L'Hopital's rules and methods, folks. We need to stay on top of that. So, again, I do present some of that here to help refresh your memory. We are going to come back with a couple more videos over the calculus of vector-valued functions. What we need to look at next is some application of limits applied to vector-valued functions, and that is going to bring about what we saw back for scalars, and that is the derivative and the antiderivative, or the integral calculations. We're going to see that in our next set of videos. And then from there, we're going to get into the application of those derivative and integral calculations. So, Again, folks, I hope you're all hanging in there. This is just the first of a few videos this semester. We will be back with more, most certainly. Hopefully if you have any questions, you can always get a hold of me. Like and subscribe on my YouTube channel. That's where these videos are posted. And I guess I'll see you next time with more on the calculus of vector-valued functions. So, see you all then.